We have added a multi-rotor interface to the Heliceal software, which allows several rotors to be modeled in the same interface, to obtain results based on the interactions between the rotors. We will see here, for example, the multi-rotor interface for the design of a thruster. With an upstream propeller assembly, here, and with a downstream propeller which will exploit the induced speeds of the first propeller, to increase the performance of the system. Here we have loaded an airplane propeller model from the model list. Here, it is a propeller which already has a fairly honorable efficiency of 0.83 in propulsive efficiency. Here, it evolves with an operating point of 200 km per hour, and a rotation speed of 1000 revolutions per minute. We will see how to use this first propeller upstream and design the second propeller, and the duo of counter-rotating propellers which would be best suited to this propeller. We have selected a propeller model, which we designed. It has rather good performance, and therefore we must start. We will say the design of contra-rotating propellers with already a pre-designed propeller with good performance. I will refer you to the propeller design tutorials with Heliceal to already design the first propeller. Once this first propeller is designed and recorded, we can load it and build a second contra-rotating propeller using the multi-rotor interface. We go to the File menu, Project Counter-Rotation, and we load the multi-rotor interface. So here is the optional multi-rotor interface, therefore counter-rotation, which has just been activated. Here we have the upstream propeller, which corresponds to the propeller that we have chosen as a model, and has been designed automatically behind downstream, a contra-rotating propeller, whose pitch angles have been optimized to exploit the induced speeds of the first propeller. The induced speeds of the first propeller, the upstream propeller, are visible here, so it is a propeller whose operating point is 56 meters per second from 100 kilometers per hour. So we see here, bottom left, that the axial input speed into propeller 1 is 56 meters second, and there is no tangential or vortex flow supplied to the first propeller, so 0 here. If we select the first propeller, we see in the graphics the elements concerning it which light up in fluorescent green. So we see here that the output of the first propeller, prop 1 outlet meters second, we have 62 meters second. This is the axial speed of the fluid leaving the propeller. We also have a tangential velocity component which is 28 radians second at the exit of the first propeller. The second propeller will therefore be supplied with this axial flux of 62 meters second and this tangential flux of 26 radians second. So we will immediately notice something. This is because the power supply of the second propeller by the first propeller is subject to a coefficient of influence which varies depending on the distance between the two propellers and the diameter ratio. That is to say that if the first helix is at a distance greater than 0.25 times the diameter, we will have a tendency to feed which will decrease. That is to say that it will have less tangential flow and less doped axial flow of the first helix. So we have here on the right the information on the influence factor, therefore the power supply of the second propeller, which varies. Here, we can see them in this area of the propeller parameters. So automatically the software creates its first and second propeller, and we can of course export them in 3D images and STL formats. We can therefore analyze what is happening at the level of these two helices. Here we see the performance in terms of thrust and the overall performance of the two propellers. We have the power consumed at the trees, therefore the overall consumption at the tree We have kinetic power and propulsive power. I will refer you to the definitions in the other tutorials, and on the design of normal propellers, and we also have an efficiency parameter on the right, kinetic efficiency, and on the left, propulsive efficiency. We note that the total overall propulsive efficiency is the average of the two propulsive powers of each propeller. So if we had an upstream propeller which was 0.83 in propulsive efficiency, and 0.92 for the second propeller doped by the first, we have an overall system efficiency of 0.89. Then an element to note in terms of kinetic efficiency is that the kinetic efficiency of the first helix and the kinetic efficiency of the second helix, therefore doped by a tangential flow, can sometimes arrive at a slightly kinetic total greater than 1. So that's physically impossible. We can just see here the result of rounding errors, and that also gives us the overall accuracy of the system, and we believe that we will never have a return greater than 1. The efficiency greater than 1 on the downstream propeller is understood by the fact that the energy which is entered into the downstream risk is boosted by the tangential flow of the upstream propeller, and therefore we have an efficiency which here can be greater than 1. We can change the overall operating point here. Here we will see what happens if this system no longer evolves at 200 km per hour but at around 100 km per hour, at 28 meters per second. So here we see on the left that the operating point for which the geometry of these two propellers was designed is no longer active. We are therefore outside of design. So we have at this stage, because we have changed the operating point, as for the single propellers. We also have the same thing. We can either calculate the off-design performance with the changed operating point, and the geometry still adapted to the old operating point, or rebuild the geometry of the two propellers so that it is best adapted to this new operating point. So we're going to do both here. We are going to calculate the new performances excluding design. So of course, these performances have decreased in terms of efficiency. Since we are out of the design point, the blades no longer function optimally. We could decide either to restore the operating point to the optimum point, or to reconstruct the geometry of these propellers so that they are adapted to this new operating point. So that's what we're going to do here and now. For example, we will increase the rotation speed. We will go to 3000 RPM, so normally, the timing will be much lower. We are going to rebuild with this new operating point, and observe the timing on the first propeller, the upstream propeller. In this position, we see that since it rotates faster, the optimum timing has been effectively reduced, and the timing also by the second propeller has been reduced slightly due to increased rotation speed. There we are, we can study these two propellers interacting according to the operating parameters. So on the right we see that you can change different propeller settings, but not all settings. We will say certain restricted parameters such as the diameter, the number of blades, or the drilling axis and the length of the axis. So these parameters are not numerous. There are not many choices of modifiable parameters. You can't really change the propeller geometry here in the geometry settings. So if we wanted to go further in modifying the upstream propeller, we would have to edit it to reopen it in the main interface, in the form of a propeller project. And there, we modify our propeller under all the parameters that interest us, and we could therefore apply it to the multi-rotor project. Once we have modified its geometry. Same thing for the Swallow propeller. I select these parameters here. I could therefore edit it again, in the Heliceal software, to modify certain parameters, that is to say, for example, I could just want to modify its geometry in terms of the shape of the generator, and I would like a curved generator, so that it makes a little less noise and eliminate intersection beats. So, let's quickly admit, and so I apply it to my project, which I'm going to rebuild. And I'm going to see my downstream propeller, which has been modified, following my recommendations. For all the propellers that therefore appear in the multi-rotor project, we can select the propeller and save it as a template. Let's say I like this propeller, I'm going to record it. In terms of model, it's there, it's downstream propeller. We're going to save the propeller model. So we're going to call it test2. And so here we see, in the interface, that we can choose and select other propeller models from the loading interface. So here, let's admit that I want to load another propeller. Selecting any propeller from our models to load it. For example, here, in Swallow Helix, we will try. But hey, of course, we can clearly see here that we are looking for a propeller that is barely 127 mm with an 1800 mm propeller. So we understand that the interaction between the two helices is not going to give us a very interesting result. So on the other hand, we can very well reload the model that we had saved just before here, called test2. And therefore we find our propeller that we had saved. So we notice that when we save a model from the multi-rotor interface, this model will be found in the list of models. Here, in the drone models list area, the multi-rotor interface is also used for the design of multi-rotor drones. Everything that is saved in this interface will end up in the list of drones. We can directly access the save folder. Here, when we select a propeller, we see where its save folder is located. So we can very easily go and find this element there and save it wherever we want on the computer. So it's just for convenience. What is recorded in the multi-rotor interface will therefore be classified in the list here of drone props models. One interesting thing perhaps is that we can notice that when we start a project, so from scratch, if I destroy my system here and I load a model from the Helicial interface, I take here the classic model of airplane propellers. When I have created my model, and I am going to enter the multi-rotor interface with a model, what is important to note is that in fact we are creating at that moment a contra propeller rotary, as stipulated here, which has the same diameter, the same number of blades, same chord distribution as the model. So this is the propeller that is supposed to go best with the upstream propeller. So we really recreate a contra-rotating downstream propeller according to the geometric parameters of the first. So here the downstream propeller has the same dimensions as the upstream propeller, which can be interesting to see in terms of performance here. Overall, the role of the second propeller is to straighten the flow, to ensure that, at the exit of the propellers of both propellers, there is no longer a tangential flow. Here, it's in this graph on the left, bottom left. So we can see the different axial and tangential speeds on each of the propellers. We see here in red. To the right of the speed graph, in red, the tangential flow at the outlet of the last propeller, at the outlet of the system. So we see here that we still have a little tangential flow. This would mean that the second propeller cannot completely straighten the flow. So we could make our second helix straighten the flow more. To further straighten the flow of the blades, I'm going to adjust the downstream propeller to 5 blades. And there we see that we have reduced the tangential flow at the output, which will result in an overall efficiency result which will be better. So here the propulsive efficiency is 0.90. If we go back to 7 blades, we are at 0.89 because there is still a little tangential flow at the outlet. That's it. This is the kind of little detail to help with optimization that must be followed when making a contra-rotating propeller. It is therefore an interface to discover and to test. Here is the end of this multirotor exploration tutorial. It's up to you to discover and create your propellers using this new interface.